Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is something completely different. Last Friday, I was working on pink noise, and it was correct, but super slow. And I promised that today I would figure it out and make it fast. But I decided to take a detour because we have this plan of working with Justin Johnson. The username of that person, in case you don't know him, is Justin, written backwards on the REAPER forum. And the plan that we have with him is to go over the code base for REAQ, which, in case you don't know, not to be confused with the stock EQ plugin in Reaper, this is REAQ without an A, just like this. And Justin is the developer of REAQ, and we are planning on going over the code base and talk about all the magic that he's pulling off in this, which is one of the best looking and most awesome JS effects out there. And this is an EQ. So we already covered filters and EQ. For a while, we have been doing that in our JS effects library, but we implemented the most common, most basic filters that are the RBJ filters, probably the filters that most people begin with when they're implementing biquads. But that's not the filter in REAQ. REAQ is using this different version. It's also a biquad, so it's the same spirit, same theory behind the filters that we have implemented already, but it's using this other thing called SVF. And the main difference is, as far as I understand, the fact that this reacts better to very fast automation. So if you're changing the filter cutoff and doing a filter sweep, this is going to react better than the RBJ filters. It boils down to numerical stability when you're doing computation with floating point numbers and you're changing the coefficients very fast. Bo is here. Hi, Bo. Yeah, it is going to be fun. So I wanted to have this conversation with Justin, and I wanted to go over the code base of REAQ with him, but I want to know the least I can. I want to know a little bit of what this is all about and implement it myself so that we can dive deeper and focus on interesting things like how he's doing the graphical user interface and the extensions that he built on the SVF filter that we are going to implement today. So Justin has implemented smooth interpolation and higher slopes instead of just the default slope that we are going to see. So today is all about an introduction to SVF. And first things first, I keep saying SVF filter, and it is something that people say, like, look at this, it's in the documentation. But SVF stands for state variable filter. So calling it an SVF filter is the same as saying ATM machine or SEO optimization. It's just wrong. And I keep doing it. And I probably will do it 1,000 times in this stream. I know it's wrong. SVF is for state variable filter. So what is a state variable filter to begin with? Well, you can see here there is a link to a PDF. That's how I even started to learn about SVF. I didn't know this thing was a thing before I dived into the implementation of REAQ. And so, as I said, it's a biquad filter. It is going to sound the same and look the same for the most part, except for fast automation. There may be other differences as well, but we already know what this is all about. It's just a different implementation of filters, so we are going to expect to have some coefficients and to remember some previous inputs and outputs of the audio signal, that sort of thing. Let's look over these papers. In case you don't know, this Cytomic company is, well, there are maybe more people there, but I know that at least there is this one guy, Andy Simper, and he is the developer or the main developer behind the glue compressor in Ableton and EQ8 in Ableton. And EQ8 is using these filters, the SVF, And that is the same filter that exists in REAQ and then in our library, because he developed a EQ8 along with Ableton, and he released the formulas to the public, which is awesome of him to do. But then again, it's written in these technical papers. They are deep and dense. It's not a walkthrough of how to implement a filter. It's for the initiated. So our main job today is to figure things out based on these papers. And there are several of them. There are more things in here, not just the SVF. That's the one that we are mainly interested in. That's the one that is linked in the REAQ documentation. There are other gems in here. For instance, there is this one that has been published just last month that may be a better version of the one that we are going to implement. Unfortunately, it doesn't really say what's the purpose of this. It just starts with like, here are some equations. And then for people who know what these equations are, then it's going to be great. But for people like us, human beings, regular human beings, it's going to be like, what? Why? What's going on? But never mind that. And there are other kinds of filters as well, like this kind of filter here. Never heard of it. Different kind of filter, not SVF. Seems cool. I don't know what the purpose of this is. Whatever. Just wanted to point out that there are more things here if you're so inclined to dive into this. But let's go to SVF. So a state variable filter, I did a quick research on this, and it is a kind of analog filter, and this is what it looks like. So these things are electronics. This is a multiplier or an amplifier. It's essentially just a multiplication. This is essentially just addition. This is ground. This is a capacitor. That sort of thing. So you can do filters with analog components if you follow this diagram. And the cool thing about SVF is that it is called the universal filter because there is this circuit and you connect the components in a certain way, and if you tap out of the circuit in particular places, you are going to get different filters. So I don't know exactly, but let's say if you get V1, which is this part of the circuit, if you just put a wire there, that is going to be, let's say, a low pass filter, and this is going to be a high pass filter, and that sort of thing. I'm not sure if V1 is a low pass and V2 is a high pass. Just saying that you can combine the outputs of the circuit in particular ways to create all the regular shapes of filters. So with a single circuit, you can implement all filters you could want for. Now, it's important to note that these filters are completely dependent. So if you have, let's say, a low-pass filter and a high-pass filter on the same circuit, there are some things that are the same for both the low-pass and the high-pass. For instance, the cutoff frequency. They are going to be low pass and high pass that complement each other. They have the same cutoff frequency. And if you wanted to change the cutoff frequency of one filter, you are changing the cutoff frequency of both. So if you want to implement a regular EQ with, let's say, 16 bands, you cannot pull this off with a single one of these circuits because you don't want your 16 bands to be related to one another. You want them to have independent cues, cutoff frequencies, gains, and so forth. So you probably want 16 of these circuits and maybe even 32 because you want to process things in stereo. Right. So what Andy did, as far as I understand, is he started with this diagram, which is the analog circuit, the idealized one nonetheless, right? It's not an actual circuit. You can just buy some capacitors and op amps or whatever, and you can build this. But as far as I understand, Andrew started with the idealized capacitor, one that behaves 100% correctly at all times, whatever the amount of energy is going through it. So you start with that, and then you transform the components into equations that relate inputs and outputs. So again, it's a mathematical definition, a model or an idealized version of those components. And then you have to solve these equations, right? You come up with equations that model this circuit, and you have to solve these equations. And that's what this paper is all about. It's using a technique called trapezoidal integration to solve the circuit. And Then this is, what is it, like 20 pages or something? How many pages? 32 pages. So it's 32 pages of Andrew explaining all the concepts, but in a very terse way. It starts with an equation. And then there are also some plots. And some of these plots don't really make sense to me. I'm not really sure what this plot is about, but there are some plots that we recognize. For instance, this one. So if you take a sawtooth and you then you low pass the sawtooth, you bend past the sawtooth, and the high pass the sawtooth, and this is what the waves look like. And yeah, this is something that we can look at and it makes sense. I mean, if you are only passing the low frequencies, then this high frequency change is going to be smoothed out. And same for high frequencies. So if you are only letting the high frequencies of the input pass through, you're going to see these sharp edges like they are here, but you are going to miss some of the nuance here on this slope because this slope is relatively low frequency. And then you see that you are losing that information. So that one makes sense. It's a time domain kind of signal, and there are even all these other ones. And oh, this is cool, isn't it? We can see the time domain effect of an all-pass filter. Because remember, all-pass means that it's going to pass all the frequencies just the same, but it's going to mess with the phase. And we do see a different shape to the wave. Cool stuff. And then there are these diagrams which are, well, these are frequency diagrams, frequency spectrum diagrams, and it's showing the gain of a low pass with a bit of resonance. But I don't know what the blue and the yellow are, and of course there are no labels. So go figure. But it does seem like it's only amplitude, it's not talking about the phase, and there are some differences that we can see clearly. So in yellow, we can see the so-called cramping or warping of the frequency domain when you're reaching the Nyquist frequency, because when you're at the Nyquist frequency, your magnitude needs to be 0, so you cramp or warp the frequency response to get back to 0. And in blue, it seems to be the idealized response, which does not warp and does not go back to 0 at Nyquist. So this here would be the analog version, or alternatively, you may oversample to get this kind of frequency response. And that's what Justin is doing in REAQ. If you play with REAQ, you're going to see that there is no warping of the frequencies. In fact, why don't we give that a try real quick? Where is my Reaper? Yes. Let's drop REAQ in there, and the band does not warp. But maybe if I go to economy mode, it is going to warp. Yeah, see? In economy mode, it's warping. It's distorting the shape. Cool stuff. And it's closer to the analog. Of course, if you go up to the oversampled Nyquist frequency, it's going to warp just the same. But that is way above the spectrum that we can hear, so it's not a problem. Right, so then there is a bit more graphs, and it's showing the code to draw the graphs. I'm not sure what the language this is, maybe MATLAB, I don't know. Let's get to the part where we can understand stuff. Right at the end, saving the best for last, right at the end there is an algorithm for every response. This algorithm is what we are going to implement. It's very similar to the RBJ paper, or not really a paper, it's just a cookbook. Similar to that in spirit, easy to follow, it's just code, and there are even some notes here on what you can do with it. For instance, you can do modulation, you can change stuff like the cutoff frequency and the Q, and the filter will remain stable even if you do modulation of these parameters, and even very fast modulation like audio rate modulation Audio rate means that you are modulating these parameters on pretty much every sample, and it's still going to be smooth. There may be some aliasing and other side effects, but yeah, as far as I understand, that's the main selling point of the SVF, or at least of this incarnation. All right, so this is the code, and let's figure things out here. There are some sections. The clear section, it is like our init section. It's just starting things off. Or if we want to maybe change the cutoff frequency in the queue, or in our case, we are calling it reconfiguring. At least that's what we called in the RBJ filters. We are calling this reconfiguring the filter. When we want to reconfigure the filter, this is what we do. We just initialize some variables. Then this set is essentially what we're calling reconfigure, where we compute coefficients. And these are formulas for low pass filter, band pass filter, high pass filter, notch filter, peak filter, and so forth. And remember, this is going to be every response with a single algorithm. So similar to what we did with the RBJ filters, we are just going to compute coefficients differently for each of the bands or for each of the types. And then over here, we're going to compute the same algorithm for everything. So let's look at the formulas real quick. So this is just initializing some variables. And for instance, the low pass filter, we need a tangent, pi, a cutoff frequency, and a sample rate. We recognize everything in here, a Q. And in this case, there is no choice between Q and bandwidth. Now, naturally, we could convert between them, but we're probably going to just go with Q for this one. And then everything else is just formulas based on the previous variables like G and Q and K and so forth. And then we can keep going, and we may see something like on a bell, there is power, that's straightforward. The bell gain, so again, the gain that we are going to apply on the bell, cutoff frequency and sample rate. All looks reasonable here. Square root, and that's all right. So that's what you need to do to compute the coefficients. Then how do you use the coefficients? I think that even the most important coefficients are these guys. I think that these ones are intermediary variables. They're not really used when computing. So in theory, we don't even need to store this. But we do need to store those. And then to actually filter a sample, as a sample comes in, what do you need to do? This tick block. So this is what is probably going to be in our sample block. And, or better yet, in the function that is actually going to filter samples. So how does that work? Well, you just have to compute some variables. And in this case, the inputs are V0. The sample coming in is V0 in this case. It used to be X of N in the cookbook and in many other places in digital signal processing. This is V0. Maybe because it is voltage. After all, this is being modeled after an idealized version of an analog model, so maybe it's voltage, that's why it uses the letter V. And I'm not even going to pretend I understand why this variable is named like this. Input, current to equalize, I don't know, who knows. But so we have our input, and then we calculate V3, and then we need to remember V1, V2, and V3, and V0 for later. No, V0 we don't need to store, but we need to store V1, V2, and V3 for later, because check this out. We are going to compute V1 based on the coefficients. That's all right. V2 based on the coefficients. And, oh, maybe we don't need to store V1 and V2 for later. We only need to store IC to EQ. And IC1 to EQ and IC2 to EQ. Yeah, because there is no dependence between these variables. Good. So then finally you can put this output, and this output is going to be the sample that we produce, the filtered sample. And again, the output here can be a high shelf or it can be a low pass. It depends on how we configured the coefficients. So the principle is the same. We are going to keep some variables around our previous outputs or previous inputs, and it's not exactly in the same form as the RBJ filters. The coefficients are organized in a different way, but it's the same spirit. Just keep some old outputs around, or intermediary outputs in this case, and keep some coefficients around, and you're good to go. So let's dive in and start writing some code. I'll leave the reference here above my head. And well, the first thing I want to do is maybe rename some stuff. Because right now in the library, we are calling just filter biquad, and the RBJ filters are biquad filters, and the SVF filters are also biquad. So this name is not perfect. We should be more specific and say that these are the RBJ version. So how about we do a global replace real quick? Or maybe even, so we have 138 results for this search. And for this one, we have a couple more. Okay, we'll see. So if we have just filter by quad, let's see if all the occurrences here make sense. And then we can do a global replacement. Well, first of all, let's see all the files that we're going to fetch, because, yeah, this should only be our files. So our naming convention is so weird, but never a bad idea to check. Okay, so I'm going to replace all of this with filter RBJ, or filter biquad RBJ. And I think it still makes sense to have a biquad in the name, because we may have other kinds of filters like single pole filter, or filters that try to model some old analog gear that we may want to have in the future, and they may not be biquads. Maybe. I mean, you can model higher order filters by a series of biquads, but let's not get into that. So global replacement, and I'll also look for the plural and do some renaming. Yeah, now that looks good. And then let's save this, or commit this. So now let's go below RBJ. Let's say that RBJ is like our first one. So this is the end of the RBJ section, and let's have state variable filter SVF. And as a reference, let's paste this in. Very similar to the REAQ code, isn't it? It's going to be the same formulas, but it's going to look a lot different because of the way that we are doing this. For one thing, REAQ is using pseudo objects that we are trying to avoid in our library. So we will need to have an initialization thing, a new to create the data structure, and a configure, and then a filter. So we're going to need pretty much the same functions, but they're going to behave differently. So let's split the screen and start writing these things. Well, maybe I can even copy the whole section. Let's copy the whole implementation here. And naturally rename all the RBJs into SVFs. I am aware that there is a better way of doing this, but maybe I can pull it off. There is a quicker way of selecting all the occurrences of a certain term in a certain range. But never mind that. SVF. So in terms of the data, first thing we have to remember we need to put this in the initialization section. In fact, I think I'm going to extract this into filter init. Great. This is super important because otherwise we would have not defined our data structures. Right, so what are the things that we need to remember? I'm gonna do it like this. So first, the type. That is a big deal. So we have a low pass, we have a band pass, but we don't have two flavors of band pass like we had in RBJ. We just have band pass. Then we have high pass, and then this other flavor of band pass goes away. We do have notch and peak. It's called peak in this case, so I'm going to rename it. Then all pass. Then bell. I'm not really sure I understand the difference between... Hanging there. Peak and bell. What is the difference between peak and bell? Oh. I'm already making mistakes, aren't I? Let's go over this again. Low pass. Check. Band pass. Check. High pass. Check. Notch. Yes. Peak. Great. All. Awesome. Bell. Not really sure I understand the difference between bell and peak. We are going to implement this and then we are going to run it and then we are going to put the Burton EQ analyzer and we're going to see the difference. Low shelf and high shelf. And that's it. So it seems like we have pretty much the same flavors as one would expect because there are only so many flavors of filters, right? Then in terms of parameters that are inputs that we want to remember for debugging purposes or even for visualization. Oh, okay, so Bo knows the answer. Peak goes up to a point and bell has a flatter curve. Peak has a more pronounced resonance. Great. Thanks for explaining, because I didn't know. Right, so besides the type, we also need to remember some other things, like the cutoff frequency. I'm going to call this just frequency. The sample rate, I don't need to store because the sample rate, if it changes, it's a global change. Our effect is going to be reloaded. It's a whole thing. So we don't need to store that. And then the gain... I wonder if I should call this variable cutoff, but I think I'm going to call it frequency because that's what I called the other one. And in fact, on the RBJ cookbook, it wasn't even called frequency. I think it was called F0, and I called it frequency because I liked the name. So there you go. So we do have a gain, and the gain, Bell dB gain, that's all right. And then we do not have different types of width. So our field here is just going to be Q, and we can get rid of all of that. Then, oh, okay, Bo is saying that for a bell, you need to provoke a resonance. Okay. So in terms of variables, we need to store, like the coefficients that we need to store. We don't need any B's, but we will need some A's, and we'll need some M's. And in terms of A's, we are going to have A1, A2, A3, and they're not normalized. So one thing I want to say is that as far as I understand, the RBJ filters are written in this form called direct form 1. Direct form 1 is a way of make a correspondence between the Z transform, and it gets complicated, but it's in direct form 1. Let me show you this Wikipedia article is great, explaining the biquad filter. When you know what a biquad filter is, then this is a succinct explanation of everything you need to remember, like these formulas. So direct form 1 is recognizable. This is pretty much the equation in the cookbook that we implemented already. It's just a bunch of coefficients multiplied by the previous samples, xn, xn minus 1, and xn minus 2, and the previous outputs. So a's are coefficients and y's are previous outputs. So as far as I understand, the RBJ cookbook is in this thing called direct form 1 that makes a difference equation. We talked about difference equations yesterday, I think. No, on Friday. So it's a difference equation that has a correspondence between the difference equation and this thing, which is the Z transform of, or just the frequency domain in the Z domain. The Z domain is a whole story. We'll get there. And I'm not exactly sure, but I think that these filters that we are implementing now are in this version, direct form 2. So 2 different circuits for the same thing. And I think that's why we have different names for stuff and why the equations are shaped just ever so slightly different. But it may not even be direct form 2, but maybe something else. What do I know? Right, so we need to remember A1, A2, A3, and we need to remember some M's, M0, M1, M2. And I am tempted to not store capital A, G, and K. We didn't store them before, and it was just fine. It's just an intermediary variable for the coefficients. So yeah, I'm happy to not store A, G, and K. But I will need to store the ICs. So let's store... We don't need to store the V's, which is kind of interesting, but we need to store IC1EQ, IC2EQ, and that's all. Let me double check if I have some mistake. It seems to be fine. Yeah, so let's move on to the initialization thing. So this is the definition of the data structure. Now let's write a function that creates one of these data structures. And for that I want a bit more of screen real estate. And so this is the definition of the struct, and then we do have a type, and then a frequency, and then gain. And these two boil down to just Q. And then the coefficients that I pretty much can borrow from here. And then dive in there. And oh, I do need the number of lines to be the same for Visual Studio Code to do the thing that I wanted to do. So I have 8 things here. So 1, 2, 3, 4, 5, 6, 7, 8. And because the number of lines match, I can do it in one pass. Great. Now let's think about the values of initialization. The type, the frequency, and the gain are inputs. They are undefined until you configure the filter. The coefficients are also undefined, and then we know that these variables need to be 0, but I could say that they are also undefined, and then I zero them as part of configuration. No, I think that doing that would not be good for when I want to interpolate different coefficients. So yeah, I'm just going to leave the IC to 0. So I guess there is a correspondence between the clear and the new function. And there is a correspondence between set and configure. So let's dive into configure. We'll need a filter, we'll need a type, we'll need a frequency. We'll not need these two. Just have a Q there. So let's make it bigger. We have type, frequency, gain, and Q. Those are the inputs. And then for local variables, this is the core of the changes, I suppose. So we are going to have G, K, A1, A2, A3, M0, M1, M2. And maybe that's all. Then we can get rid of a lot of things in here. But I do want to keep this part. So how about I do it like this? I'm gonna find this. And then get rid of all of those. Nice. And then let's match this with the types that we have. So pretty much these types. Low pass. Then band pass. Then high pass. Then notch. Then peak. Is there a difference between peak and band pass? Not band pass. Between peak and bell in REAQ. Did just implement both of them. We have peak. We have some other flavors of high and low cut that it's not an SVF. So low cut, Butterworth, and analog are not SVF. Then we have shelves, notch, band pass, tilt, shelf. This is not part of the SVF. Pultec low shelf, not part of SVF, and all pass. So Justin decided to implement peak and not bell. Ha, cool. I didn't know this one existed. This is actually something that we can do with RBJ or SVF. It just boils down to having a low shelf and a high shelf controlled by a single node. The same with the Pultec, by the way. We can recreate this with a low shelf plus a band here. We just have to calibrate everything correctly. But we can do this with RBJ and SVF. Yeah, it's just, I think that just the Butterworth and the analog are not SVF. Right. So continuing, low pass, band pass, high pass, notch, peak, all pass. Then we have a bell, low shelf and high shelf. Great. And then I think comes a time where I should have that song that I wrote for when I'm doing something boring. Should have that queued, but I don't. I need to configure OBS to do it for me. Haven't done that yet. Because I'm going to start doing something boring, which is to copy the formulas. But before I even do that, let's move on and pretend that these formulas are implemented, because they're essentially copy and paste. Nothing too terribly interesting. We don't need to normalize this as far as I understand, but we do need to store all this stuff. So let's go up where we initialize the filter, and then we need to store all these guys, not IC1 and IC2. These we don't store. But we need to store all the other ones. Just like that. And I can do this. And there you go. Now, to actually filter a sample, we need to receive the filter as well as the sample. We will need to retrieve all of these people. I think that may be all. Yeah, right. So let's actually retrieve all these people. That did not work well. Okay. Okay, we retrieved the variables we'll need. We'll also need a couple more local variables for this one. Let's refer to the formulas. So each tick is like a clock ticking as samples come in. And this is the number of multiplications and the number of additions. Cool stuff, huh? We are doing a lot of memory access, so multiplications and additions, they are free. This thing is going to be a bit slow, maybe. We'll see. So we'll need V1, V2, and V3. Oh, and actually V0 as well. Let's have a variable for that. V0, V1, V2, V3, and we have the ICs. And I think that's it. Yeah, great. So now we have all the coefficients. I will have an output as well. And I'm going to output the output at the end, just like that. And then over here, we'll do the formulas of V0 and blah, blah, blah. See you on the other side. Okay, let's double check. Don't you just hate how Reaper puts tooltips even when you're not in front of Reaper? Like, see this track, input, blah, blah, blah. This is a tooltip from Reaper, but Reaper is not on top. And still, it's putting tooltips. Don't you just hate that? Does it happen to you too? I hate that. Okay, double checked. It seems like everything is all right. Now, we do need to store this IC1 and IC2 to EQ for later when we are going to filter the next sample. And super importantly, we need to say that V0 is equal to the sample that is coming in. And we need to do that before this line. So I think that this implementation holds water. I think that this is what we need. But we still need to implement the formulas, right? So here's something. I am going to cheat for a while. I'm just going to say that all of these are to do. I'm doing this just so the program is syntactically correct. And I'm going to implement the low pass and we are going to look at it. So let's just implement the low pass, and I may or may not do the rest on the stream because it's just copying some formulas. I don't expect any surprises. Tangent is a function that comes with REAPER. We don't have to do anything for that. Pi is written like this in JSFX. Our cutoff frequency is called frequency, and the sample rate comes with REAPER. It's called S rate. Then this is 1 over Q, 1 over 1 plus okay, double checking. All right, let's test this out. We need another page. We do have, oh, this page is called filters by quad. It should be called something that has to do with RBJ. Let me figure this out real quick. By quad, RBJ. And then when I show the title of this page, let's go to the GFX block. Okay, so with that, I have a proper title for the RBJ section. So how about I have a section for SVF now? Filters by quad SVF. And then I will have sliders for all of these values in the demonstration effect, but like for the type, for the gain, for the frequency, for the Q, I'm not gonna have it now. I want to speed things up because I want to see this filter. So let me just go to the page of the RBJ and have another one for SVF. And then let's see everywhere where we are using this. We're using it to show and hide sliders, that's all right. And we are also using it to actually filter stuff. I really like how these two are so similar. That is a good point. I think that we are doing good work here. In terms of design, I think. Keep writing SVG. So you may have noticed that I cut myself. You see that? I cut myself doing the pedal board that we did with Arduino on the stream and everything. Yeah, so now I have an enclosure for this and I cut myself doing that. I'm terrible with handwork like that, but check this out. It's my pedal board. But I cut my index finger, so typing is harder today. And I didn't even try to play the guitar, but it's probably gonna be hard. Then we also need to initialize the SVF filter, so I'm gonna do that here. Now let's go over the code real quick and see if we're missing any RBJs that should be, or even, yeah, any RBJs that should be SVFs as well that we should copy and paste. So we do have some slider section that I'm just want to completely skip over. And it seems like I remembered everything. Great. So, oh, one thing that I did not do, thanks, Bo. One thing that I did not do was to configure the filter, right? Because I'm doing that in the slider block for RBJ, but I'm skipping the slider block for now. So I will just real quick configure this here. I want to put a to-do here. I keep adding to the list of to-dos. I very rarely remove stuff. Even the SVF filter is here on the list of things to do. Right, so add sliders for SVF. Keep writing SVG. And then, oh, how about I have an init filter is equal to that. And then I configure what type do you all want? Low pass, of course. It's the only type we have. What frequency do you all want? How about 1000? And gain does not really make sense for a low pass. I don't think. Yeah, it's not used here. We didn't use this variable. Gain doesn't really make sense, so I'm gonna just pass undefined. And then Q, I don't think Q makes sense. No, Q does make sense. We used it there. So Q can be 0.707. If you know it, you know it. This is a value that 71, right? Because it's rounded up. But 707 is a value that makes this slope have a certain property that I forget. But it's a value that comes up often. So I think that this does it. It's configuring the filter. Let's review our changes real quick. Over here, we only changed that. And over here, we are only adding stuff. So that should be right. Great, let's commit and then let's test this. Looking forward to that. So master is muted, that's great. Then let's drop our lovely Burton EQ curve analyzer. And then drop our effect in there. The curve analyzer right now is it's empty. That's cool because we are now on the white noise generation with a very low gain. But if I increase the gain, then we start to see some crazy stuff happening. Because it's trying to analyze this thing as a filter. It's not a filter. Right, so let's go to SVF. And I am in the wrong page. All right, oh yeah, I forgot to change some numbers. Yeah, we have 2 page 10s. That's no good. And this slider is now going up to 12. Let me double check. Yeah, I think I forgot to change this later. In fact, this number, as far as I understand, is ignored by Reaper, which is kind of odd. It takes in account the number of elements in the list. It does not take in account this number here. Okay, and there you have it. This is a low-pass filter, ladies and gents. Now, I'm not really feeling like copying the rest of the equations now, but we do have an understanding of what's going on. The rest of the equations are going to be not super interesting, I don't think. I hope it won't be interesting. I'll just copy and even create these sliders off stream, maybe, probably. I don't know. In any case, I see you tomorrow and we'll do something. We may get to the pink noise. We may, if there is any peekaboo in the SVF, we'll talk about SVF. It will be fun. I see you tomorrow. Thank you all for being here. Thanks for being active on the chat, for supporting me on PayPal and Patreon, for being awesome all around. And I see you tomorrow for more of this JS Effects programming. See you tomorrow. Bye.